Hello everyone, my name is Mehmet Kurum. I am Assistant Professor at Mississippi State University, Department of Electrical and Computer Engineering. I'm also Co-Director of Information Processing and Sensing Laboratory, IMPRESS Lab. I am pleased to have you with me today, and I would like to welcome to our presentation entitled A UAS-based RF Testbed for Water Utilization in Agroecosystems. I would like to thank the conference chairs and program committee for organizing this session and providing us this opportunity to share our research. Also would like to acknowledge our contributors, IMPRESS Co-Director Dr. Gürbüz, graduate students, undergraduate students, and postdoctoral associate listed here. And this work is in part sponsored by USDA ARS, Engineering Research Development Center in Vicksburg, Mississippi, and NASA at different capacities. So here is the outline. I divided this presentation into 6 parts. In the first part, I'll talk about our introduction and motivation. Second, I will introduce the RF sensors that we have been developing. And I'll talk about ground truth and logistics to verify the results. Talk about the physical models. I'll talk about the information retrievals, and I'm going to have final remarks at the end and introduce you to the microwave farms concept. All right, introduction and motivation. So there are 2 questions. What do we measure and why do we measure? Well, let me start with why first. Why do we do this research in the first place? Well, first of all, agroecosystems compose large economic sectors in dominantly agriculture-based societies. Availability and management of water resources have a huge influence on sustainability of agroecosystems. For instance, low soil moisture is a major constraint on crop growth due to its vital role in providing crops with sufficient nutrition for root uptake. In short, we want to know water availability and environmental stress for estimating plant productivity and potential yield. In particular, we are interested in estimating top soil moisture, top 5 centimeters, and deeper into the soil moisture, we call that root zone soil moisture. We can use this information to help forecast crop productivity. Furthermore, soil moisture reserve should be taken into account when choosing a fertilizer rates. So current methodologies in precision agriculture are insufficient for direct soil moisture sensing, since reflected shortwave solar radiation and infrared longwave emission can only provide information about the surface characteristics. On the other hand, microwave remote sensing can provide deeper penetration into the soil and as well as the vegetation. In addition, the frequency that has been used for microwave is much more diverse compared to the optical remote sensing. So I will say the key difference is the type and number of sources is used. For example, for the current state of science, they use either sun reflections or long wave emission. And penetration is another difference, and of course the spectrum diversity. So in this talk, I'd like to summarize our efforts to apply radio frequency micro remote sensing from UAS for water utilization in agroecosystems. All right, let me start with soil. So the soil is like a sponge, so they can hold a certain amount of water. And if you know the amount of water in the soils, and if you know that there's a big rainstorm is coming, for example, and the soils are near saturation, and we can predict that the area might be a risk for flooding. So obviously, too much water or too little water is a problem. So we would like to, track the water. We want to understand, where the water is so that we can plan. And it's a really critical information, particularly for agriculture. So currently, there exist satellites that study Earth's moisture content. For example, SMAP, soil moisture mission. And it can provide you the Earth's soil moisture content, and it can tell where it is, where it comes from, where it goes. and it provides you a view how the whole Earth system works. However, such a system, satellite system, is providing a two-course resolution, data in two-course resolution in time and spatial domain. And mostly these data is not really useful for individuals or small farmers. So in this research, we are focused on bringing this technology that has been applied from a satellite scale and bring it to the hands of people using low-cost and ubiquitous sensors. And I will illustrate the use of active, passive, and signals of opportunity agriculture remote sensing from ground and low altitude system. So the promise here is that we want to develop an instrument that is immediately available and transferable for infusion in largely agriculture-based societies in order to make an impact. So how do we do those? Well, first, let me talk about the microwaves a little bit more. Here is the microwave oven in my own kitchen. So the microwave ovens use microwave radiation to warm food by making the water molecules vibrate at certain frequencies. So basically, the energy generated by the magnetron penetrates into the food, and it then cooks the whole food simultaneously, not just from the outside. But how does it work? Well, our food is filled with water, so we expose the food to electromagnetic wave, and water tries to align. It's polarized, so it tries to align with the radiation of electric field. Then the oscillating electric field racks the water molecules back and forth rapidly, and molecular friction creates the heat. And in this figure, this is like I said, is the microwave oven in my kitchen, and its size is not really arbitrary. And the cooking cavity where you put your food only reflects the waves of a length that fits into an oven. So it's not really arbitrary size. So I go ahead and measure the length of my oven and counted the peaks and valleys and estimated my estimated wavelength approximately. And the frequency is the speed of light divided by the wavelength, and I got an answer about 2.5 gigahertz, which is not too bad for primitive measurements like that. But in actuality, the microwave oven operates at 2.45 gigahertz. So something has to be special at that frequency or around that frequency range. Well, think about this picture. So what is this? So you might want to say this is a food, right? But from a scientific perspective, well, in fact, it's a mixture. So similarly, the Earth's surface vegetation are a mixture of various ingredients, like your food in this picture. Soil is a mixture of mineral particles like clay, sand, loam, organic matters, air, and most importantly, water. Similarly, vegetation is a mixture of dry matter, air, and water. So the interaction of electromagnetic wave with Earth's surface and vegetation can successfully describe using the material's effective dielectric constant. Particularly, the dielectric constant of a liquid water and dry soil is completely different, as there's a large contrast, and that large contrast is the key variable to quantify land surface properties. Again, the main driver for dielectric constant of natural materials is the water, and in fact, the water in any phase. So here I show you surface reflectivity at L band 1.4 gigahertz as a function of angle and also at different polarizations for three distinct cases: pure water, wet soil, and dry soil. It is evident from this figure that there's a large dynamic range depending on the amount of water in the soil. In fact, this dynamic range is the reason why we use the microwave remote sensing. And in fact, these properties are well known. Microwaves are highly sensitive to water within the plants and soil. However, its implementation from small UAS platforms are at relatively low technological readiness level compared to use of traditional shortwave, longwave optical sensors. So here, in broadly speaking, we divide microwave sensing into three categories: active, passive, and signals of opportunity. So the active is a typical radar. You have a transmitter receiver on the same platform. And the passive is just measuring the emitted radiation coming from the surfaces and measures the brightness temperature. An active one measures the backscatter. And the third way is the signals of opportunity. In fact, this is the one is gaining considerable attention within the scientific community in the last decade. In this case, this is also called passive radars. Your transmitter and receiver are well separated, and this system is called bistatic system, and it measures the reflectivity. In this system, the transmitter is the existing infrastructure, could be a communication satellites, it could be navigation satellites, and you invest your effort in building and processing the receiver to measure the reflected signal. All right, now we'll look at each one of them and understand a little bit more. Here is the illustration of a traditional microwave remote sensing implementation from a ground and UAS-based platforms. Here is the radar, sending the signal and then receive back the signal from the vegetation on the ground. Here is the radiometer that measures the microwave emission coming from the vegetation. And all of these scenarios, we have side-looking antenna. That's a typical use. And here we are also building a ground-based radar system to validate our results from a drone-based systems. And this one illustrates the signals of opportunity reflectometry. It's also known as a passive radar implementation from UAS platforms. So the receiver collects multiple reflections from these existing transmitters simultaneously, which increases the coverage considerable compared to traditional active-passive microwave sensing. I'll talk about this in more detail. All right, here are this slides includes the RF testbed instrumentation that we have developed, or some of them are in development. So we have ground-based radar, we have UAS-based ground penetrating radar, we have smartphone-based GNSS-R. Again, I'll talk about those in the coming slides. We have P-band receiver, we have commercial dual-channel GNSS-R reflectometry, we have low-cost GNSS-Reflectometry, we have drone station, we have rovers. So this is part of the instrumentation. I'm going to highlight a few of them in these talks, and I'll be happy to talk more offline. If you have interest in any one of those, I'll be happy to talk to in more detail. All right, let me give an example from GNSS-Reflectometry. So GPS, right? That's a part of that. And GPS signals, GPS are designed for positioning and navigation. So positioning, so you need to know X and Y, your coordinate, which is X, Y, Z, and you need to know the clock bias between your phone and between the satellite. So there are four unknowns in theory, and you're trying to solve that unknown. So you need four equations. So if the four satellites are visible to you, so you can solve this equation, you know where you are precisely. However, in real life, things not that easy. So there are a lot of error sources. For example, atmosphere, ionosphere, and multipath. So that's why you need more than four satellites to know where you are. But we are interested in those source of errors. In fact, those source of errors are the source of informations. And in particularly, we're interested in the multipath. All right, so these are called speculative points, reflection points, and contains information about the surrounding of that stationary receiver. But stationary receiver is not really a great interest. So think about that. You put that receiver into a platform, moving platform. So those multipath points are moving with you as well. So in case of GNSS constellations, there are like hundreds of satellites are available, and 40 or 50 of them are visible to you, And if you use those as your transmitters, you will have 40 to 50 different specular points on the surface. And when you scan, when you move with your drone or small satellite, you can scan really large area. You can cover large area in short period of time because of that number of available transmitters. Okay, I'm gonna give an example. All right, so in this example, we use smartphones, right? Particularly Android smartphones that have providing you the GPS raw data. So we integrated the smartphone to the small UAS to sense the water. So in this sample, we also place the phone to a gimbal to stabilize its position and to minimize the errors due to the motion of the drone. So here the red is the red line is the flight path, and these ellipses are the specular reflection tracks associated with one satellite only. Again, you can show many, but I don't want to make that crowded, so that's why I have only one satellite shown in here, and it's overlaid with an aerial image that we collected. So these colors are the signal strength. So the blue color is the highest and the yellow color is the lowest. And it's very clear that over the pond you have a high reflection, and as it's going over a field, it fluctuates depending on the amount of vegetation and the soil moisture. And as it passes through this small creek, the signal level is going up again and then fluctuates again. And this is done with a simple smartphone attached to a very small drone. And you can see the power of reflected signal and sensitivity to the water. Second, this is a more comprehensive experiment still ongoing that with USDA. We would like to map the soil moisture over entire field and collecting multiple satellites over a long period of time. So we collected data over 5 to 6 months. We also collected optical data as an ancillary data to provide some of the information that we need to train our models. And in particular, the canopy height, vegetation water content has a significant impact on the reflected signal, and we use LAI and DVI as the indicator of the vegetation amount to train our models. And our interest is soil moisture. However, the soil texture and roughness also has an impact. So here in this map, you can see that a map that we generated based on the reflection data that we collected. And of course, we collected some ancillary data as well. So this is ongoing, and we're starting a new experiment this new season as well. And we hope to collect more data and share our results and methodology in more detail in the future. This is another instrument that we are working on, and in particular, like I said earlier, we are interested in the root zone level soil moisture. So to accomplish direct measurement of the soil moisture at greater depths, lower frequency signal should be used to probe farther into the soil, because the penetration depth is inversely correlated with the frequency. So the lower the frequency, the higher the penetration is. So in pursuit of direct measurement of root zone soil moisture, so we developed a UAS-based P-band reflectometry. We're using the military MUOS satellite constellation, which transmits signals at 370 megahertz as our free transmitter, and we place antenna to top of the drone and bottom of the drone, and we isolated direct and reflected signals, and we collected them separately. And we correlating the direct and reflected signal, we are retrieving the reflection information over the ground, and in fact deeper into the ground. So this platform is composed of an octocopter with a wingspan of 137 centimeter long, and it carries like 20.8 kilograms. So it's fairly large drone. It's a proof of concept. It only flies 8 minutes with this payload, but again, this is a proof of concept. So we did some check with the system. For example, the two key checks. One of them is the presence of the the signal waveform in the power speckle density. And second, we check the spike in the cross correlation of the two channels, direct and reflected channels. And that has to be at the lag, delay, which corresponds to specular delay. This pad is longer than that pad, so you can figure out from that. And the results indicated that the receiver is operating correctly. So this instrument, again, still under development, gonna bring us one step closer to direct measuring the root zone soil moisture. And utilizing the platform like this and some simulation tools, we feel like this is gonna lead development of more complex inversion algorithms and high quality data products in near future. All right, I want to talk about the physical models a little bit because the physics is the essence what we're doing here. All right, here in this slide, what I show you is the how do we link the measurement to the parameter of interest, right? So on one end, you have measurements, could be passive emission, radar emission, or signals of opportunity reflectivity. On the other hand, your parameter of interest, you might be interested in the height of the vegetation biomass or the soil moisture. But this relationship is not that simple. So the system parameters like the wavelength, polarization, incidence angle, and resolution, as well as other structural target parameters are impacting the signal. So for that purposes, we develop forward models, which require a lot of input parameters to estimate what should the output is. Also, we develop inversion models either based on a simplified physics or machine learning or combination of both, and to estimate the parameter of interest from the microwave measurements. So here I summarize the mechanisms for first order backscatter contributions, zero order emission radiation at microwave frequencies, and specular reflection. So in modeling radar backscatter, the three main contributions dominate. All right, these are volume scattering, double bands, and surface scattering attenuated by the vegetation. And the relative contribution of these scattering mechanisms can vary significantly depending on amount and type of vegetation, soil roughness, and moisture conditions. As far as the passive remote sensing is concerned, zero-order radiative transfer model, known as tau mega model, has been widely utilized. So the microwave emission from soil is attenuated and scattered by the vegetation, while vegetation contributes its own emission. Here are the three mechanisms you can see in here. And a reflected signal acquired by a signals opportunity receiver are generally superposition of both coherent and incoherent scattering, in addition to the direct signal that it might be receiving. So our simulated analysis indicated that the specular component contains the greater portion of total energy and thus contributes more to the received power. So the reflected signal can be modeled as just a specular reflectivity like that. All right. So to investigate all this potential that I mentioned, so we developed a generalized fully polarimetric forward model. We call this SCABE. We also developed a simulator framework that employs this model to create analysis environment for community of researchers, scientists, and users with little or no electromagnetic background. So we aim to enable studying, analyzing new methodologies with varying configurations and determining optimal cases for precision agriculture applications and generating, visualizing, analyzing test data with the help of this model. And this model is free and open source. In fact, we develop tutorials, we develop documentations that provides a lot of details about the model for newcomers to this field. Here is an example from that model simulations. So in this simulation, we use GPS satellites that are illuminating a cornfield, and we have a low altitude receiver looking down to the cornfield. And since this is a simulation, we simulated the entire growth of a corn from beginning plantation to the harvest. And as the vegetation grows and then decays at the end, the signal strength is changing about a 6 dB because of the change in the vegetation water content. And for a given vegetation stage, we change the soil moisture from dry to wet, and we observe 6 dB changes. And for given soil moisture and vegetation water content, we change the surface roughness as 2 dB. So the received signal is about 12 dB dynamic range, which is a very large dynamic range that can be really utilized to sense either vegetation water content or soil moisture. Okay, now I'm going to move on to the ground truth and logistics. So collecting ground truth data is important for verification of the data that we collect from the RF sensors. And unfortunately, collecting ground truth data is not easy and laborious and time consuming. And it also leaves substantial room for human error. Or it can provide you some limited observations. For example, here in this example that we generated, we use 8 soil moisture probes to train our models. But what we want is really want to develop, and this is in development, we develop a rover system which has 2 sensors. One is RFID sensing system. Right here is the antenna. The other one is the contact sensing system. The RFID sensing system uses the moisture sensing passive RFID tags to read the soil moisture at certain location throughout the crops. And contact sensing system uses a soil moisture probe, sticks into the soil and collects the data. And the rover travels into the field and makes the map like this. And this is in progress, and we hope to finish this and get the map and compare our UAV results. But there are some barriers with the UAS measurements. There are 2 key barriers. One is the limited flight time of the drone operations. The second is the limited on-site data processing resources. So recently we developed a drone station, we call it Nest, to operate drones with indefinite flight operations in an integrated single system. In fact, Nest is a self-sustainable, solar-powered, full autonomous mobile trailer platform that contains 2 autonomous drones with customized drone sensing modalities and 2 landing base stations for battery swap and data transfer. In fact, Nest acts as a logistic hub for drones in remote places. So when a drone docks, it can dump the data it has gathered onto Nest's computer system, and this allows the Nest to become a centralized hub for data collection. We think that this system will gonna greatly improve our data collection and gonna make it very systematic, and a lot of data we expect to collect using the system. Information retrievals. Basically, we can utilize 3 strategies to maximize the vegetation and soil moisture retrievals. Number 1 could be physics-based only, data-driven, or hybrid approach to maximize the positive characteristics of both physics and the data itself. So we know that the information retrievals from agricultural environment is very challenging for many reasons. And relying on physical models alone, for example, can result in inherent biases due to incomplete information, unmodeled parameters, or simplifications made for the sake of computational complexity. In comparison, machine learning model techniques are often difficult to manage due to requirement for site-specific information, which can lead to an insufficient amount of data for learning, training, and validation. So what are we going to do? Well, what we're doing is, what we're planning to do is, we want to integrate both physics and data-driven worlds for enhanced sensing. How do we do that? Well, our plan is what you can do is you can explicitly integrate physical information into machine learning by investigating the physical relations into the loss function. Second, machine learning models can be initialized with the physics-based simulated data. And again, this is something ongoing, and so far we use the physical models and we use data-driven models, And now we are working on combining these two to improve the accuracies of our estimations. All right. Finally, my final remarks and future perspective. And I want to particularly place emphasis on sensing the soil moisture at multiple depths using signals of opportunity. And I call this concept microwave farms concept. And this concept originates from our desire to bring satellite technology into hands of ordinary farmers, thereby to foster access to reliable, timely, and accurate information and to guide them as they manage their own land. So how does the microwave farm concept works? Well, the microwave farms can repurpose existing new space infrastructure. You have thousands of free illuminator operating at different frequencies from IPLSC XKU bands, and coupling these free transmissions with widespread availability of smartphones and inexpensive drones, we can create decision-making systems for unified and ubiquitous irrigation and water resource management in agroecosystems. So this concept basically try to answer two questions. What information is already available in the surrounding environment, and how can it be exploited for remote sensing, in particular for the precision agriculture? So we envision that the microwave remote sensing from small UAS platforms can enable non-intrusive high-resolution soil moisture estimates at multiple depths of soil, as it has a potential to be a powerful augmentation to the traditional thermal and multispectral imaging capabilities due to comprehensive features. Thank you very much. It was a pleasure to talking to you, and I'll be happy to talk to you more. These are my contact information. Thank you very much.